Mm-hmm. Hmm? The you well, I do not know. I'm gonna have to look it up. Okay. So I'm going to kickstart the class. This is your homework assignment. Okay, so today's lab is about structures, and it will give you, and you have to write the code to do something like this. The due date is next Wednesday. I know it is one day before Thanksgiving, but it is also one day before Thanksgiving, which means it is not Thanksgiving. So that means, I am still expecting people to be working on their school stuff. Okay. And if you say, but I have to help people, prepare for Thanksgiving dinner and whatnot, then do the homework earlier. I mean, this is how you study for this class. Okay, so if people say, "Oh, I'm just gonna look up the earlier, like the video from last year, when I talk about the solution of this homework assignment," Do do I hide those videos from people? No, because once again, it is not my grade. It is not my student loan, and it is not my job. Okay, so people have to kind of decide for themselves what is good for you. Okay, because it's at the end of the day, it is you, right? Not me. All right, so what we'll do today is to take a look at this code. I won't give you the code of the most important part, which is the function, but I will give you enough to get started with this homework assignment. Okay, so that's what we're going to do today. So we are going to start with a command line interface. Okay, this one looks good. Might need to kind of shrink it a little bit just so I can fit enough stuff. Okay. So I'm going to basically create a program like this, but it's not exactly the same. So we'll go ahead and create the struct4.c. And I made a really stupid mistake today in CISP 300. It is so stupid. It is so funny. I laughed at it. Um, I wrote a program in C++ to illustrate how to use your structs. Okay, not even class. Okay, it's just struct. And it wouldn't compile. It's like, why is it not compiling when I try to pass a struct by reference? Okay, and I check all the syntax, check all the spelling, they're all correct, and then I realized that passing by reference is a C++ only feature, and I was using GCC, which assumes the language was just plain C instead of C++. Yep, that was my mistake. I forgot that I've been using just GCC, instead of G++ for C++ program compiling. All right. So I'm just replicating the code here. You guys can kind of relax for a little bit when I do this, but it's not going to be long until I'm done here. All right. So node is defined to be a structure. It has two members. The first member is v, the second member is n. V is the easy one. It is simply an a-bit unsigned integer. It can store values from 0 to 255. N as a member, on the other hand, is kind of a little obscure, right? Because it is a pointer to a struct node type. Okay. So I think in the previous class we have already talked about how this is okay because all pointers are how big in TTP? 1 byte, exactly. So it doesn't matter whether it's pointing to a structure or it's pointing to an integer or pointing to whatever. All pointers are 1 byte wide in TTP. Okay. So now we look at this, kind of messy thing here. Okay, this is n1 as an array, and it is basically an initialized array of struct node objects. Okay, so I'm going to follow exactly the same thing over here. Okay, this is n1 bracket 1. And even though you may not know how to express this in assembly language, you should be able to understand the meaning of these few lines. It is initializing an array of structures. So we have 10, the address of n1 bracket 3, and then we have 4, the address of n1 bracket 4. And then finally, we have 9 and 0. Okay. Oops, 9 and 0. All right, so I'm just gonna pause here to make sure that we understand what is going on. Okay, so when you look at what a node, what n1 is, n1 is an array. Okay, that's what the square brackets are for, of struct nodes. It is not an array of pointers to struct nodes. It is an array of struct nodes. So we are going to construct what the memory layout would look like in this case. So that means this line or line 9 is initializing element 0, and then line 10 is initializing element 1, element 2, element 3, and then element 4. So for each element, it has two members. 5 goes to the first member, which is V, and then the address of some node, struct node in the array is going to be initializing n over here. So that's kind of the structure of this thing. And then we have, so for our purposes, I'm just going to put everything in main. U in 8 underscore T. We have X. Okay. All right. So we have X, just X is fine. And all I want to do is to add up all the values. Okay. So if you look at what the first element has, or element 0 itself has a value of 5, V is 5. It contains the address, okay? N is the address of the next element in the array. What about the next element, element 1? It has a value of 3, but it also contains the address of the following element, which is the element 2. Element 2 has a value of 10, but it also has a way to find element 3. Element 3 has a value of 4, but it also has a way to find element 4. And then element 4 has a value of 9, and then it has a null pointer to indicate that, yep, I'm the last one. We are done. Are we good so far in terms of, how the elements are set up to quote unquote find the following one? Okay. Yep. Yep. Yeah. Yeah. So null, null in all uppercase is just a fancy way to say zero. Hmm? No, it's literally zero. Zero is typeless, which means 0 can fit spots where you expect a double, you expect an int, you expect a bool, or you expect a pointer of any kind. You don't have to cast it before the compiler says it's okay. Now, if it's non-zero, if I stick a 5 here, oh, the compiler will be upset about it. But 0 is one of those things where, oh, okay, it's fine because 0 is 0, regardless of the scalar type, it is still the same. So it doesn't need typecasting to do it. Okay, so this is where we're gonna do like, okay, x is initialized to 0, and I need another local variable here. So this is node, and it is a pointer of some kind, ptr, and then we'll say ptr is going to be the address of n1 bracket 0, the first element of the entire array. And then we have a loop, okay? We set up a loop, and we say as long as PTR is non-zero, we'll do the following. What are we going to do in the following, in the loop body? We are going to say x plus equal to PTR points to V, and then PTR itself becomes PTR points to N, and that's the code. Return 0. There we go. All right. So this code should add up all the values, all the V members of the entire array. So that's going to be 18 plus 13, which is what, 31, I think. So it should be 31 in X when we get to the return statement. All right. So only one way to find out. Okay, we don't need this anymore. I'm going to close this part. Okay. Instead, I will extend this one. Okay, so we'll go ahead and close this. GCC-G-O struct4 dots, and then struct4 dot C. Compile the first time. Okay, cool. And then we list the program, put a breakpoint on line 25, run the program, and then we say, okay, tell me what x is. Aha, 31. Okay, very good. So 31 is the summation of all the V members of the 5 struct nodes in the array called N1. Are we good? Okay. But we also want to check things out a little bit here. Okay, I say print N1. Aha, okay, it does print everything here. So now we can say, okay, tell me where N1 is. Okay, that's where N1 is. And then I'll say ask where is X. Okay, so do you see a kind of main difference between the address of N1, which is an initialized global variable, as opposed to X, which is a local variable? Do you see how the addresses are really different? This one is not even on the stack. N1 is not on the stack. Global variables and static local variables are not on the stack. They are statically allocated, which means their location, the compiler will determine their location and done. Okay, they are not on the stack. They are not offset from where the stack pointer points to. Okay, so now we're going to take a look at the assembly version of this code. Okay, so we're going to quit here for now and then copy struct4.c to struct4.ttp-asm. Okay, there we go. And we do the usual thing. You'll basically comment out everything. So substitute the beginning of a line with slash slash with a space. And there we go. All right. So there's nothing to do with pound include standard integer.h, simply because in assembly there is no type to begin with. Okay. So now we only have to redefine a node itself as offsets two members. So member V is the first member. It has to start with an offset of 0 from the beginning of a struct node. And then node underscore n, which is the second member, is going to be the offset of the previous member plus the size of the previous member. And then we have node size, which is the offset to the last member, which is n, plus the size of member n here, which is 1, because it's a pointer. So are we doing okay so far? How lines 7, 8, 9 are really corresponding to the struct node definition. Okay, all right. So now this is the fun part, okay? This is the fun part because we have N1 as a label. So now all we need to do is to say, this is just going to be a byte, which is a 5. So that 5 is matching this 5 over here. And now we have to specify where we're supposed to find the next member, right? There are a few ways to do it. One way is a dot 1 plus. Because it's literally the next location, right? So we can do it this way if you want to, but if you want to rely on labels to do it, then you can go ahead and say, okay, it is n1 underscore 1 because it is member 1 of n1, which makes this one also n1 underscore 0 because the beginning of the array is also the where you can find the first member of the array. Is that okay? Are we doing okay? I can illustrate this using the debugger in GCC. Do we want to do that or not? Okay, we have some knots. Okay, let's do that. Okay, so I'm going to put a, so whenever I have to stop, at a certain point, I just put a little bookmark so I can remember, where to resume my work. So that's just something that I do. Okay, so we're going to go back in GDB struct4, put a breakpoint at, so this time I don't really need a particular place, so I can put a breakpoint on, like, let's say 919, that's fine. As long as the program is in execution, I'm good. So we are looking at N1, okay, where is N1 as an array, okay? That's its location. So now we ask where is the first element, which is element 0 of N1, the same location. That's what I'm talking about. Are we good? All right. So now we can go back to the assembly code, okay, and continue. All right. So now we can put this here as n1 underscore 1, which is basically saying element 1 of n1. And then in the C code, it is a 3, okay, byte 3, followed by, n1 underscore 4. This is n1 underscore 2. Sorry, I look at 2 and then I set 4. Yeah, habitual liar, right? I mean, it's more like misinformation. I would make a great spy. Don't tell me anything important, but I will tell the other side as if everything is important, and they're all wrong. All right, so we are almost done here. This is byte, uh, what is it? 9, followed by a 0. Okay, so byte 0 is the pointer, the member n of element 4 of n1 as an array. Are we good so far? Do you know how hard that is to remember what I just said? Once the genie is out of the bottle, it is out of the bottle. Uh, is that about the 0, the byte 0? So the byte 0, this is the value of member n of element 4 of n1. In other words, this is the value of n1 square bracket 4 dot n. Hmm? Nope, it's a null pointer. It's pointing to nowhere. Yep, yep. And of course, for those of you who go like, I really like to see the word null. Fine. All right. And because the assembler is case insensitive, if for those of you who who's absolutely wanting the same look as C++ or C, okay, fine, you can have your null back. Okay, cool. So now we put in some extra code, okay, the entry code here, okay, no op LDIA with dot 6 plus, decrement D. Now I do this, kind of semi-automatically because I already know the sequence. But for people who are really just kind of trying to understand the code, don't do it like as if, oh, okay, I'm just copying the code. Make sure you can explain the role or the job of each line of code. Okay, it's important to do that. All right, so now we go to main and we try to figure out what main has to do. Okay, so here's main. And main has got two local variables. Okay, x is the first one, and the PTR is the next one. So that would be main x 1 plus is the offset to the previous one plus the size of the previous variable. And then main LVR LVS, it would be main underscore PTR 1 plus, okay, not node size plus, because PTR is a pointer to a struct node, not a struct node itself. Okay, so that part is important. All right, so we have the two local variables offsets already done. So that means I need to do the allocation and then the deallocation and then also the return code. So, pretty standardized stuff, okay? But from your perspective, it is always good to explain to yourself what we are doing here, why we are doing this, how does this relate to the concepts in C, okay? So now we add it back, and then we can now do the usual return, which is LD, BD, increment D, JMPB. There we go. All right. So do we have any questions up to this point? This is the usual way that I set up a function, okay? Nothing particularly tricky up to this point. So are we good? Okay, we're good. All right. So now we look at x equals to 0. Okay, so pretty standard stuff. LDI A with 0, LDI B with the offset to the variable, and then add the stack pointer to the offset so we can get to the actual address of that thing. and then we do a st to that location so that we update local variable x to whatever a has. So that's done. And then the next line initializes the stack pointer. I mean, not stack pointer, but the pointer to a struct node. So LDIA, which is the right hand side. This one is surprisingly easy. That's all we need because N1 as a label is representing the starting point of the entire array. It is not an offset from the stack pointer because it is not allocated from the stack. It is along with the rest of the code, which also means if you overwrite anything in N1, it's going to kill the program. You end up with self-modifying code, which is not a good idea. Okay, so we have B and we put PTR, add BD, hmm? Self-modifying code. Okay, so if you want to know about self-modifying code, I can tell you about self-modifying code. So Microsoft, I'm not sure whether it was Microsoft. Yeah, it was Microsoft, but they were doing something on the Apple II computer at the time, and they were using self-modifying code as a way so that people cannot um, it's a copy protection thing, to so that it's the code to unlock the program is quote unquote cryptic. So they were using self-modifying code for that. And then when I was programming the 6502 processor, which is the same processor that Apple II's used to improve efficiency, I also use self-modifying code. Um, it's very ugly. Okay, it's prone to all kinds of problems, but it does squeeze the last ounce of performance out of that really kind of archaic processor. It's an 8-bit processor running at 1 megahertz. You can kind of imagine how slow that can be. Anyway, all right. So that's all the initialization. I'm gonna stop right here, okay? Because what I want to do is kind of go like, okay, do we know what is supposed to be on the stack? So let's go ahead and check out what is supposed to be on the stack in this case. So now we go to the share folder, okay? Same thing that we always do. Okay, I can do a Pinky impersonation, but so brain, what are we gonna do tonight? Same thing that we do every night. What is it? What is it that the Pinky and the brain would do every night? Try to take over the world. Yes. With an emphasis on try. Mm. Yeah, it's their form of entertainment. It's okay. Alrighty. So we are gonna have pull this one down. This one is not going to take up a lot of space, so that should be more than sufficient. All right. So this is the return address. Okay, return address from main to the entry code. Pretty much standardized. And then we have the two local variable of main. This is x of main. This is ptr of main. So that means these three locations together forms the frame of main when it is called from the entry code. So we are going to go, kind of mark it up a little bit, give it a little bit of color like that. Okay, put it here. There we go. All right, so this I don't know what it is. This one not yet. This one also not yet. Okay. But wait. We actually do because we have just initialized. X should be a 0, and this one should be the address of N1. Okay, I'm just going to put address of N1, and then we'll figure out from the assembler, what it is supposed to look like. So are we doing okay so far? And then the stack pointer is pointing here right now. Are we good? All right, so we're going to switch back to the code. We already have a halt instruction. Save the code, and then you'll go to the folder where Reefer Spider is located, and then we submit struct 4.ttp.asm. Uh-oh. Well, that's good. I like debugging. If it doesn't work, we're going to fix it. All right, so let's check out what the errors are. No, there are no errors here. There's no error over here. So I think it's just out of sync for some reason. Okay, let's do it one more time. Okay, this time object code is good. I didn't do a single thing. All right. I think I understand why it is reporting error, an error. I think, before it won't let me continue until the spreadsheet has fully updated. Now it is asynchronous. I think that is the problem. I can fix that, but we can fix that later. Okay, so we go to analysis and then we ask, did we put the stuff that we are supposed to put over there? Is the return address to the entry code at location 8? Double check it. So we go to the assembler and then we go to location 8 and ask, are we supposed to come back here? It is right after the JMPI instruction, so this is the correct place to go back to. All right, continue a little bit more. Okay, what else did we put on the stack? FD gets 0, 0. And what is FD? FD is supposed to be X of main. Getting a 0 is exactly what the C code is specifying. So we're good there too. And let me change the name of the spreadsheet to today's date. Today is 1119. And then we go back to the assembler, go a little bit further. Okay, we're putting a 9 into FE, which is supposed to be the address of N1. So now we go back to the assembler, or go back to the assemble tab of the assembler, and we ask, is that the correct location? So as it turns out, it is the correct location. Okay, 09 is in fact um, the beginning of the entire array, which starts with 05 as a byte, because that's the V value. That's the value of the V member of element 0 of the array. Are we doing okay so far? All right. So now we confirm everything. So now we can continue with the coding. So, it is helpful if you just kind of put a little marker that you double check and verify the code execution up to a certain point. So that way, if you also combine that with the use of get, that means you can always trace back to an earlier version of the program in case you end up with a program that doesn't work anymore. All right, so now we're going to implement the loop here. Okay, so to implement the loop, this is what I do. You can do whatever you want, okay? But I can tell you, if a program does not even assemble, it is automatically a 0 in terms of score, okay? So keep that in mind. Okay, so the way I do things is I try to be as systematic as possible. So I would start with the name of the function and then which loop it is referring to at the top level. We only have one loop, but I still use the same method. And this is the beginning of the loop, so that's how I would label it. And then I would immediately label the exit point of the same loop, because this is how I can remember that, like not to miss the end. And right before the end, I also should have an unconditional branch to the beginning, because that's what makes it a loop, right? You have to jump back to the beginning. So an unconditional branch to main underscore while 0 underscore begin, I put it here automatically. Okay, so now we have an infinite loop, which means, what I need to do now is to specify, okay, when do we exit the loop? But this is the order of how I put the code in when I have a loop, okay? I always start with the structure itself, and then I go back and backfill the detail of the structure. Because if I don't do this, if I go forward in one direction, I would have forgotten one of these two easily. Okay, so I know that I cannot track more than more than a few things at a time. This saves me the trouble of having to track all of those extra things, especially if the loop has nested statements and whatnot in it. Okay, so now we have to say, okay, we are staying in the loop as long as PTR as a local variable is not null. Okay, well, I don't care about the comparison part. because I need to get to PTR first. Okay, so we're going to get to PTR first. Okay, so we go use whatever register because we are not calling anything. So register A, B, and C are basically the same. Right. Okay, so offset address of the actual thing. Um, I'm looking at this and trying to see if I can save some code later on for optimizing, but I'm gonna let go of the optimization concept for now. Okay, so this is pointer, and I just need to know whether it's a zero or not. That means I can use and AA, okay, and then use the Z flag to branch out, because if it is zero, I actually want to get out, which is going to main underscore while zero underscore n. This is how we exit from the loop. So that means now what we have to do is would be these two statements. So I think I'm going to go with a more tedious approach first. So this is highly structured and really kind of repetitive in a way. So we need to access. So I'm going to deal with the right hand side first. So what is the right hand side specifying? It is really important that you can articulate what the right hand side expression first, because if you don't articulate, or if you don't know how to articulate, you probably don't know how to implement it. Okay, so it is important to articulate it first. It is member V, the value of member V of the structure that is pointed to by PTR. Okay, so I would spell it out. Okay, and if you need to, in when you're writing your code, comment it. Okay, put that exact sentence into the comment so you can look at the comment, read the comment as you try to implement the code. Okay, so we are looking at the value of member V of a structure that is pointed to by PTR. So when you look at the words of and also by, that gives you a sense of dependency. Okay, so use that dependency to figure out what do I need first, and then what do I need second, what do I need third, and so on. Because a lot of times the implementation of something like this, the difficulty is about I don't know where to start. Okay, and that's an indication of not knowing the dependency among the items, and being able to articulate, you know, the right hand side the way that I did is already spelling out the dependency. Okay, so I think that is important. So that means I need to get to PTR first. Okay, so we're going to do LDI. Any register is fine. Okay, PTR, get to the address, and then we get to the value. Okay, yep, yep, it is repetitive, so we can comment out the code later. Okay, so up to this point, we just go like, okay, this is PTR, and it is the address of a structure. So now I can say, okay, we don't need necessarily the first byte of the structure because I can reverse the definition of V versus N. So you cannot make the assumption that V is always the first member. I can also add an additional member before V. So don't make assumptions. So I always kind of do it like this: node underscore um, V in this case, add B to A or A to B, doesn't matter either way. I'm gonna do it this way. So now, what is in B? B now has the address of member V of the structure that is pointed to by PTR. Okay, and as usual, I do not comment my own code so that you can do it. Okay, so I can imagine a few branches here. Okay, I can imagine people who did exactly as I suggested. Okay, they comment the code that as a way to study for this class. Good. Okay, and if you phrase it in your own words, it's even better. Okay, instead of just listening to the lecture through the video and just kind of type whatever I said. Okay, so that's one. Two, some people intuitively understand all of this and they don't need to comment the code. Cool, not a problem. And then there's also the third kind, would be people who do not understand what this is about and decide not to follow my advice to comment the code. Okay, so I can spell out all the possible cases and possibly people who are not even here physically yet, at this point. So four cases. So you just have to kind of know which case you're in because that can have a direct relationship with how you perform in the final exam. I'm saying this and recording this so that people cannot come back to me and say, but Tech, you never told us how to study for this class and I'm getting a failing grade of this class. I'm not happy about it. I understand you're not happy about it. Hmm? I can do better. I can do a split screen. So you want to look at the node ones like these, okay? And then the bottom is going to be all right. So without commenting, I can still kind of track my own code. So by the time we are done with line 76, we have the address of a member V of the structure that is pointed to by PTR in register B. Uh, but are we looking for the address of that member or are we looking for the value of that member? We're looking for the value. Very good. So that means we have to do another LD, right? LDBB. All right, cool. So now B has the value of member V of the structure that is pointed to by PTR. Okay, and we're gonna check it. Okay, you go like, but how can you possibly check this, right? This program is not even done yet. Well, we have the C code, remember. So we can actually check the C code and find out, okay, what are we supposed to have, on the right hand side? So let's go back, to the C code. So we're gonna rerun the C code, gdb struct 4, and then we put a breakpoint on line 22, okay, because that's the point where our assembly implementation is at right now. And then we just run the code, and then we just print the whole thing. We just ask, what is the right hand side supposed to be? Supposed to be a 5. Are we good? Okay. Yes, because I put a breakpoint here. This is the first time in the loop, which is also corresponding to where the halt instruction is, because the halt instruction will always stop at the first iteration first. Okay, so now we go back to the assembly code, go to the halt instruction, the second one, which is here, and then we say, okay, this is supposed to be 5. Okay, B is supposed to be the value of 5. Okay, I would even comment it here. Okay, B is supposed to be 5. Okay, save. The reason why I want to comment it here is because the comment shows up in the trace. So that makes it easy for me to spot by what time what should be in which register. Okay, so if you have been commenting the rest of the code, they would also show up in the trace, which is actually really helpful from the perspective of one, debugging the code when you need to write your own code, and two, studying for this class. Because the more comment you write here, the more you're actually studying for this class. So that's at least that's the way I see it. Okay, people do not have to necessarily see things the same way that I do. All right, so looks like we are good here. Cool. And then we go back to the trace, which is the analysis tab. We look for the halt instruction at the very end. Okay, so this is the halt instruction. And then we say, okay, B is supposed to be 5. Aha, it is supposed to be 5, and it is 5. Okay, so this is how I would debug a program. Okay, you really step by step make use of the halt instruction because if you don't use the halt instruction, then you have to mentally track, okay, which line is where I'm supposed to be at. And then the rest of the program, because it's not done yet, right? So it's not going to do the right thing either. So you might as well just put a halt instruction right at the point of your last few instructions so that it's clean, the trace is clean, it's not going to take as long to kind of update and so on. So that's kind of the reason why I use the halt instruction in this context. All right, switching back, we're gonna continue with this code, okay? So now we go like, okay, this is all good, and I'm gonna take out this line here because this is inside the loop. It's not gonna be 5 all the time, okay? It's just gonna be 5 this time, but other times it's not gonna be 5. So we are done with the right-hand side. We have to deal with the left-hand side, which is, x, and we are using a compound assignment operation, which means we're adding the right hand side to the value of the left hand side. Okay, so how do we do this? We have two more registers, which is just enough to get this done. So we have LDI, okay, we have to get to X first, okay, so we have to get to X. We're going to use register A for this purpose. Main X, get to the address of that thing. Keep the address around, okay, because the first thing is read from that location, change it, and then we have to write back to that location. So I'm going to keep register A as it is. I have one more register left, which is register C. So now I do LDCA. So register A has the address of X, register C has the value of X. So now I use all three registers. I just update C um, by adding B to C because B is the value of the right hand side. So I'm going to add it to the initial value of the left hand side, and then we just store that back to wherever it came from. So that's how we not increment, but do the compound assignment in this case. Is that okay? Yeah. So it doesn't exit the loop, then it would just be an infinite loop. No, 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 no. It's not. No, that's not what it's gonna do because it will treat 0 as the location of the next node. So it will start to interpret instructions as if they are struct nodes. And it will never exit the loop because it will just kind of keep going and going and going. It won't crash. It's an infinite loop. It will just keep adding things, until you decide that it's time to quit. Yeah. All right, so I will put a halt instruction here, okay, because I want to confirm that I am updating x also to 5, because this is the first iteration. X was initialized to 0, so if you add 5 to 0, it should be a 5. So now I just say, okay, register C should be a 5, okay, should be 5. And then we also know that at this point, X also should be 5. Oops, there we go. I would check it first, okay? So we will go ahead and run it. All right, so we just scroll down here. We can see that location FD is updated to 05. The question is that variable x of main? Yep, it is variable x of main, okay, and it's now updated to 5 as expected. And then we also want to know whether register C is a 5, and it is. Okay, so we are good here. Okay, we know that we have just confirmed that instruction or that single statement in C. So now we go back and go like, okay, we can now proceed, with the next instruction. So the next instruction is the same thing. Okay, you have to evaluate the right hand side, and then you store that into your left hand side. kind of the same thing. So instead of reusing things from the past, okay, yeah, we cannot reuse anything. So we just have to recompute the whole thing, okay? Main PTR, add AD, LD, AA. So that would be PTR itself, and then we'll put the offset to the member N into a different register. In this case, let's say register B, node underscore N, add AB or BA. Doesn't really matter, either way is fine. I'm going to add B to A. So at this point, register A should be the address of member N of the structure that the PTR, the pointer, is pointing to. Okay, I can actually check it now. Okay, I can check whether that really is the case because it is supposed to be the next element of the array. Okay, so I'm going to check it. Okay, every time you can potentially check something, do it because it looks like it's a waste of time, but it's not. So now I just say, okay, register A is supposed to be the address of N1 bracket 1 because that's uh, the next element, okay, which is also known in this code to be N1 underscore 1. Okay, so this is just a reminder to myself, what is it supposed to be? How do I find it? Okay, save the code, go to River Spider, and just run it. All right, so everything looks good. And over here, okay, register A gets the value of 0A. Okay, so now, hmm, well, we can look back here, right? So 0A is this location. Uh-huh. I think it is correct. Okay, it is the address of. Okay, so I think I might have missed the comment here because I said that it is the address of the next thing, but it's not because we have the we have the address of, okay, let me rewrite this because I forgot. I forgot that I have not dereferenced it. So at this point is the address of um, PTR points to N. That is what it has. So I misspoke a little bit earlier. And then if we dereference it, then we have the actual value of the next pointer, which should be in this case um, N1 underscore 1. Okay, so save this, try one more time. So I make mistakes. Okay, I forgot one more dereference, and then when I looked at the trace, it's not matching what I'm expecting. So the question is, can I explain why it is not what I'm expecting? That whole process of looking at the difference and try to explain that, guess what? That's studying for this class. Okay, troubleshooting is a form of studying for this class. Okay, so now we go back to the trace, we go back to the analysis tab, okay? So that is correct, okay? This is in fact the address of the member end of the structure that PTR is pointing to. This is in fact the value of member end of the structure that PTR is pointing to because I can look at it from the assemble view. This is where member n is. This is what member n has as a value. Are we good so far? Okay. So now we go back to the code and go like, okay, that's encouraging. Okay. So that means this halt can go away, and that turns out to be the entire body of the loop. Okay. So save. And then we look at it and go like, oh, okay, that is the entire program. Um, so we will let it run, and then we'll see whether by the time we get to the only halt instruction, which is in the entry code, by the time we get back there, whether x ends up with a value of 31, and then PTR should be 0. Because if PTR is not 0, we should not be exiting the loop. So there are two expectations here. PTR should be 0. We should end up at the halt instruction. The stack pointer should be back to 0, 0. And and local variable x should be 31 in decimal, which is 1F in hexadecimal. Yep. Okay. So we set up all the expectations. If you cannot track all of those things, write it down on a piece of paper, type it in a text editor so that you can remind yourself what you're supposed to see. Okay. So now we make sure we save the code, run it again, and see whether it is going to do what we expect it to do. So once again, I think it's going to work, but if it does not, it's even better. All right, so it looks like it is, yeah, that doesn't look good, which is great because it means it's not working. And it does look like it's an infinite loop. All right, well, it's uploading still, but I can still see, what it is going on here. Oh yeah, definitely an infinite loop. Yay! All right. So if it is an infinite loop, you look for patterns, okay? Or you can also look for things where you go like, okay, did it get to 1F at some point? Nope, it did not get to 1F. So now you look at the pattern of what it is incrementing. So we know that it started off with a 5, okay, that's good. And then we go like, okay, what is supposed to be next to the 5? So I cannot remember the initialization. So we have to look at the 5. 5 plus 3 is supposed to be 8. And I don't think we are seeing 8. So the next update should be an 8. Aha, it is incorrect. So that means, this gives me enough information to find the bug already. So we backtrace, okay? This is the only time you can actually execute a program backwards. So why did I store a 0A into that location? It's because of this over here. So now the question is, what did I add to 5 to get 0A? I add 5 again, okay? So this is the 5 to begin with, and then I add a B to C. So whatever B is going to be wrong to begin with. So B also end up with the value of 5 when it's supposed to be 3, okay? So we know at this point the program has gone wrong already, so we have to go back up a little bit more. So we look at this and go like, okay, where do we pick up the 5? We picked up the 5 from location 9. So where's location 9? Location 9 should be the address of member V of something, okay? Should be the member V of the next item. So now we go back to the assemble view and go to location 09, and we go like, uh, it's supposed to have advanced to the next location, and we did not advance. So that means PTR is not updated because I did not update it. I just remember I figure out the right hand side and then go like, yeah, we should be good. Well, no, no, no. It's we should compute the left hand side. So I have a theory about what went wrong. Okay. So the next thing we need to do is to confirm, right? So there are two ways to confirm it. You go to analysis and then you just ask, am I incrementing by am I doubling every single time? Because that's no, no, it should not be doubling. It should be adding 5 each time. So after the 0A, it should get 0E because A is 10, E is actually 14. Mm. Oh, 0F is good. Okay, that's 15. And then after 15, we should get 20, which is a 1, 4 in hexadecimal. And that's what we're getting. Okay, so that means we are not changing PTR, and that's why it keeps pointing to the same node, and we are adding the same 5 over and over again. Problem solved, right? That is the process of debugging. Okay, if there's anything that is really super duper important in any class that you take, it is how to think. It is not about TDP. Okay, who else is going to use TDP? Nobody. Okay, no one at work. Okay, no workplace is going to use TDP. Um, who's going to use a spreadsheet like an assembler? Nobody. Okay. So what is the value of this class? Troubleshooting and how to map assembly code, how to map C code to assembly code, because that gives you an insight of how things are organized in a C++ program, which actually give you extra tools for debugging your C++ program by the time you get to CISP 400 and 430, and you have pointers pointing everywhere, and then things get overwritten when it's not supposed to. This will give you a slight extra edge in terms of debugging those programs. All right, well, getting back to the program, we know what the problem is, so we can now fix it. So we did this is computing the right-hand side, and I got so excited, I go like, oh, we are done. No, we are not. So we now have to kind of update it. So this time I am going to do a little bit of fancy stuff here, okay? So I am going to put this in a different, I don't want to destroy register A, okay, in the process. So I can now reverse these two and then just say this is B and this is also B. So with that change, that means the last time I update something is on this line over here, which is still not exactly what I need. I can now use another register, register B. Oh, no, I used that already. Register C then. Okay, so this is me doing fancy stuff because I'm optimizing. Because now, what is so this is also good exercise. Okay, this would be a perfect place for you to practice commenting because it requires you to track what is in each register from line 18 all the way until we are done. The last time we update register C, oh, okay, I forgot one more thing. This is supposed to be C. There we go. So register C is continuing to be the address of PTR. Register A is the content or the value of PTR. And then register B is the entire right-hand side. Okay, now all we need to do is to store to wherever PTR is supposed to be, and we still have maintained that information in register C, and then we just have to store register B to register C in this case. So that should advance it to the next item. This time, because of the previous example, I'm going to put a halt instruction here. I could tell by how much time it takes to upload the trace and go like, no, that doesn't feel right. All right. Well, with the halt instruction, it will be quick anyway. So we just go to the halt instruction and then we ask, are we storing why are we storing 0B to location FE? So we look at the stack layout and location FE is PTR of main. And by this time, it should be storing the address of element 1 to that location. So now we have to check out where is element 1 in the array. We can find that out in the assemble view. So this is the location. It is supposed to be 0B. So now the question is, are we storing a 0B to location FE? Yep, that we are. So that's a confirmation that we now, we are updating PTR itself correctly as the second statement inside the while loop. So now we can go back and just kind of let the program finish its job, take out the halt instruction, okay, and also take out this comment over here because it's not fixed to it's not fixed to the first element because it would just kind of move on to the next element, and so on. So we just save the program and then repeat the whole thing. Now we don't have the extra halt instruction. Okay, doesn't sound too bad. Okay, so we're gonna see if we are advancing. Okay, 1F, and then we get to the null pointer. Okay, that's a good sign. Are we exiting? Yep. We're getting to the halt instruction. The stack pointer is back to 0, 0. The last thing that we store to um, local variable x is 1f, which is our 31. The last thing that we stored into PTR is the null pointer, which is correct. That's the reason why we exit the loop. So now the whole thing is working. All right. Questions? Okay, cool, cool. Now just remember, if you thinking that you understand it here when I'm talking about it is one thing. It's a great sign. It's a good sign. It does not mean that you can replicate the whole thing on your own. So it is still important to use some form to record what I just said. Okay, take notes or watch the video again. And I will send you the code. Okay, so this way you also can comment the code so that you know what each line is doing. Okay, you figure out what each register is containing. Why do we need to update the register that way? How does it relate to the C code? That is, I would think that's a useful exercise. All right, so let me do exactly that. Okay, and this is zip. We'll call this struct4.zip, struct4.c, struct4.ttpasm. So we are I'm giving you both the C code and also the TPPASM code. And the way you look at this is to basically see how the C code translates to the assembly code. With every single line in assembly code, you should be able to figure out how it relates to the C code. That is the key, is how does it relate to the C code. All right. Okay. And announcement 2025 1119. See, this is struct 4 C attached. Okay, there we go. Struct4.zip. There we go. And publish. All right. So we have about a little less than 20 minutes left. So let me show you what you need to do for the assignment that you are given with. So yours is obviously not as simple as this. And let me show you what yours look like. It is a function call and it's recursive. I think I had that zip file already downloaded. Let me. It is struct 2, I think. Is it struct 2? Where did I put it? Yeah, I can do it again. So the lab is really simple. It only has 3 points. The homework is the complicated part. Exactly. All right, but I do want to give you guys as much as I can. Okay. So yours, oh, it is struct 2. Okay, so I was right. Okay. So it was struct 2, unzip, struct 2.zip, and we just overwrite all. There we go. All right. So we'll take a look at the C code first. Um, edit anyway. All right. Yep. So this is what we saw earlier. And when you look at this, the complexity is going to be this one single line. So now the question is, what is that one single line doing? It is basically what we just did, except it's done in a recursive way. It is recursive because it calls function f, calls function f again. Okay, It's similar in the concept. Yep. Okay. So we'll check out what this is going to do. Okay. So we'll check out what this is going to do. And I think I forgot one thing. Did I forget something? Yeah, I forgot one thing. Y should be initialized to 0 first. Forgot about that. Okay. It starts with a value of 0, but it really should be in the code. So I'm gonna rezip the whole thing and put it back into the instruction. So we'll go ahead and kind of run this code and make sure that it returns with the value that we think it should be returning. All right, so gcc-g-o struct2 gdb struct2, and then we put a breakpoint on line 24, run the code, print y, it is 31, and x should be 31 as well. Yep, there we go. Okay, so that's what the code is doing. It is a recursive version of what we just did. So let me update it first. Okay, so we'll do a zip dash u, I think, struct2.zip. Yep, it picks up the corrected code automatically. And I think the assembly code also needs to be updated because I give you the main already. So main is already done. And yep, okay. So I need to change this too. So main y, add ad, ldib with a 0, stab. So that would initialize local variable y to 0 first, and then it will pass it along. Okay, so that should do it. I'm just double checking the code, making sure that I'm not missing anything. That's the second one. This is the first one. Okay, so I think we are good here. All right, so now we rezip the whole thing, including the assembly code, and go back to the question. And remove link. And then we just have to relink it, which is insert. I think I can do it this way. Yeah, yep, okay. So it's updated. And then I have to do one more thing because Canvas is notoriously annoying because I have to click two things to update the entire thing. I have to update that, and then I have to update the whole thing. Update the question first, and then update the quiz as a whole. Okay, so that's updated correctly. Now we can go back and look at the code and ask, how do we implement struct2 the way it is? Now, I never really changed the struct2 itself. Okay, so struct2, oh, this is not the struct2 that I'm looking at. There we go. Uh, nope. Hmm. That is problematic. So what struct2 is in struct2 now? Uh-oh. That's not the right struct2. All right, unzip it first, overwrite everything. Take a look at this struct2. Okay, that is the correct one. Okay, I can just talk about this one. The one that is linked in your assignment or in your quiz is okay. All right, so with this code here, how do you start the implementation? I would, if it were up to me, the first thing I would do is to, okay, The first thing I would do is to simply return this. So take out this entire thing here, just return whatever VPTR is pointing to. And but if you want to check if the code is working or not, that means you also want to change the initial value of y, make it something non-zero, okay? Because that's how you can check whether you are storing, whether you're returning the correct thing. So if you change that 0 to say 65, okay, then the return value of f should also be just 65. There's no condition. It just returns whatever VPTR is pointing to. So make sure that you can get that working first, because otherwise, nothing else is actually important. And then the next thing to do is to replace the recursive call, the entire thing, the entire recursive call, with something like a constant value, 66. Okay? Because this is how you can check whether your code is evaluating the condition correctly here and picking the correct sub-expression to return. Okay, so do not do the recursive part until you know your conditional part is working correctly. Okay, now let's just say that if everything is good, okay, and you can now go for the recursive case. The first one I would do is not to use n1 over here. I would use a 0 over here. Because if you're passing 0 as the first argument, that means your PTR is a 0, which means it should go for the non-recursive case, which is just returning 0 plus whatever PTR is pointing to. So get that working first, okay? Because if your base case is not working, the recursive case definitely won't work. Is that okay? So it is only at that time that you know everything else is working, then you can start with the recursive case. But there's a difficult recursive case and there's an easy recursive case. N1 is as hard as it can get. Okay, so what you want to do is to start with this one. Okay, start with N1 square bracket. Uh, that would be 3, because in that case you're supposed to only have one level of recursion as opposed to 5 levels of recursion. So deal with the smaller number of recursion first. If that's working out, chances are it would also work in the general case. So that means in C code. Okay, so let me see if I can still do this. Okay, we want to overwrite, I think. So open read only, edit, overwrite, recover, quit, abort, or we can just delete the swap file. I think we can. Usually it gives me an option to remove the swap file, but I can just open read only. So what I meant is this is the this is the last one that you check. Okay, the first one that you want to do is this. If your code is consistent with the C code with this change, then proceed to check out the next one. Okay, so if this one is working, then you do the second one. So the second one is simply to use the last one, which is the address of n1 square bracket 4. So this would be a one level recursion, because the first time it is going to say, okay, PTR is not null, and then the second call is going to have PTR being null. So you should only have two levels of um, two instances of function f calling itself. And then if this is working, then you can go for the next hardest one. So I would do it in this order instead of just writing everything in one shot and then try the most difficult case. hmm Oh, I can send you the practice final exam if that is what you want to do. Yeah, now that we are starting to deal with structure, you can actually start to look at the final exam and see if you can understand it. So let me do that. It's not a bad idea to start preparing for the final exam in terms of prepping your own material to bring with you. Well, yes and no, because everything really stems from two documents. The first one is the caller-callee agreement, and then the second one has to do with structures and arrays. Yeah, exactly. Yeah. So let me send you the final exam from spring 2025. See attached. All right, so is teaches exams CISP 310 1253 fx-000.pdf. Everything is structured. So that's how I can remember where everything is because everything is structured. All right, so this is what the final exam looks like. It is I give you a program. The program is on its own page. Okay, the C code is on its own page, and then I give you a faulty implementation. But I'm kind by interleaving the C code with the assembly code, so you don't have to look at a a sea of assembly code and try to figure out which one is corresponding to which part of the C code. Okay, but it does contain problems. So now the question is, can you spot all the problems in this code? That's the nature of the final exam. It's just the programming part. Yep. Some people like it, some people don't. Okay, but the question is, how are you going to prepare? I mean, you got about 4 weeks to prepare for the final exam. A little less than 4 weeks, but you got time. Uh, Okay, American River College final exam schedule. That's how I find it. Okay, so it's based on the day and also the time of day of the lecture of this class. So we are definitely daytime. The start time of this lecture is 10:30, and it's a Monday Wednesday class. So that means our final exam is on the 18th. Oh, that's it. Oh, wait, 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 wait. That's Tuesday, Thursday. You're correct. This is our final exam time. When is our calculus? You got 15 minutes in between, and it's okay. So if you want to complain about this, when I went to undergrad at the University of Hong Kong, okay, where you have one final exam period close to summer for the entire academic year. And then there are classes where they only go from September to December. Okay, so that's the first semester, and then there's no exam until the summer of the following year. Then you get the final exam of something that you last touched about 5 months ago. 5 months, not a whole year. Yes, but if you think that is hard, then think about the law students of the same university. The first year as a law student at the University of Hong Kong is known as the honeymoon year because there's no exam whatsoever in the first year. So it will be the first year plus the second year, and then they have the exam. Yes. Yep. Yep. And you can still have multiple exams on the same day. I have had that. And the high school exit examination of Hong Kong is the accumulation of, I think, about 3 years of material. It's equivalent to ninth, 10th, and 11th grade in the United States. So the 3 years of material is tested on one single day, for the exit high school exit examination. And most people take the exit examination on uh, typically 7 to 8 subjects. Some crazy people go for 9 and 10. You have a choice. So I think 7 is the minimum. But if you want to get to matriculation classes, which is the only way to get to a university, you need at least 8. No, no. Yeah, people who take on 10 subjects is because they are the pride of the family name. Yeah, yeah. You understand that? Yes, you're the pride of the family name. You're honoring all your ancestors by being able to take on 10 subjects and get A's in all 10 subjects. If you think A is hard in the United States, an A in Hong Kong is harder. Why? Because instead of having 4 actual letter grades, we have A, B, C, D, E. Those are all passing grades. And then there are 3 failing grades. F, G, and H are all failing grades, which means you can just barely fail, you can fail, or you totally suck. Hmm? It's based on percentile. It's worse. It's based on percentile. So that means that in one particular year, let's just say everybody did great in the physics, exit examination. They only take a certain percentage, like the top whatever percentage of people, and say, okay, these people are getting a letter grade of A. Yep, 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 yep. So that's where I grew up. Well, the stress problem in Hong Kong, is at the scale of jumping off a building. And it happens every year without fail. Okay, so it's not like, only a certain year somebody has a precondition to begin with, and the extra stress, just kind of push that person over the edge. No, it happens every year, predictably. Oh, that's a that's a very pragmatic way to look at it. Yes. Oh, it's no. If you fail, you have dishonored all your ancestors. And then your entire clan look at you funny. It's like, oh, Tack, you failed not only yourself, but you failed all your ancestors, your entire clan, plus all the ancestors, not just the ones that are living. Hmm? Yes.